13.1, an introduction to limits. In the body of topics that prepare you for calculus, this one lies at the heart. And we'll start with the description. It's not the definition, but it's helpful. Description. Functions have a domain and range. For many functions, when we pick x values that get closer and closer to some number a, the values of f of x also converge on a number L. Now, to discuss this, the best thing we can do is remember rational functions. Do you remember wholes? Yeah. Okay, so use any means necessary to find an example of a rational function that has a hole in its domain. This might be a good time to use the internets, which you have access to at the moment. So, find a function that has a hole in it, a rational function with a hole, a simple one, write it below. And this is the important part. What leads to the presence of holes? Okay, go for it. No, really, pause the video and go find it. Yep, you can do it. Okay, so I'm going to use the function x squared minus 9 over x plus 3. Remember that what led to the presence of a hole in a rational function was a domain restriction that could be eliminated by cancellation. So this particular sucker can be factored into x plus 3 and x minus 3. It's all over x plus 3. So the hole originates when we cancel the domain restriction in the denominator. Of course, remember the domain restriction doesn't go away. We still can't use -3 in this function, but that's why there is a hole rather than, what would be the other thing called? Yeah, it's an asymptote. This one doesn't have one. This one just has a hole. Okay, I want you to take a look at x squared minus 4 over x minus 2. And this gets to our point about limits. When the values of x approach 2, what value does f of x approach? How could we determine this? Well, graphing the function is a really good place to start. And for our purposes, especially in the current technological situation, Desmos is probably the easiest way to do it. So let's go over to a Desmos screen. Now, I've already entered x squared minus 4 over x minus 2 into the field here, but if you wanted to do it yourself, and if you hadn't gotten this far, you would use the keys down in the lower portion of the screen. Desmos works really nicely on the iPad. It also works really well on your laptop. Whichever one you want to use is great. You can also do this with your graphing calculator. So we've got this line, and we'd asked ourselves, as x approaches 2, what happens to f of x? And the line is a hint, right? We can look at what happens at 2 on the x-axis and trace that up to the y and say, oh yeah, looks like there's a point at 2, 4. But we can do an even more interesting thing with Desmos. Let's tap into our function with the gear. We're next going to click on the little spreadsheet icon. And now, suddenly, we've got a table option. This is fantastic, because the point we were interested in was 2. And I'm very curious to see what happens when I look at values that are close to 2. Like, what about at 1.9? What's the function value? Oh, it's 3.9. What about at 1.99? What about at 1.999? Etc. Okay, so you can see we are converging. The values over here are heading towards 4. That's coming up from below 2, or as we would say, from the left. Let's look at it if it's coming from above 2, or if that is from the right. So we're going to add a line down below. What about if we were really quite close, 2.001? Yeah, okay, so this confirms we're looking at the same value. And if we get a little bit farther out, because I like symmetry, we actually see the exact same pattern. So that's good. That shows us that looking at the numerical values, this function converges upon 4 when x approaches 2. Let's go back to our notes. Let's go ahead and bring a shot of what we were just looking at into this screen. Okay, great. So Desmos is a great way for checking out behavior of functions numerically. And remember, this is just a table of points. If we wanted to add in the overall function behavior, it would be that line, and we've got that whole happening when x equals 2 and y equals 4. So that's how we want to think about that. This leads us to the idea of the definition of a limit. If the function f of x approaches some value L, as x approaches the value a from both left and right, then we can say that the limit as x approaches a exists. And the notation is thus: the limit as x approaches a of f of x is equal to L. Let's apply that to the function we just looked at. For f of x equal to x squared minus 4 over x minus 2, what is the limit as x approaches 2 of f of x? Well, as we saw numerically here, when x approaches 2, we see those y values heading for 4. And that's what's happening on the graph as well. So for this function, we would say that the limit as x approaches 2 of f of x is 4. That was a pretty well-behaved function, but badly behaved functions are so much more interesting. And you know what's badly behaved? A piecewise function. So, what value does f of x approach as x approaches 5 from the right in this function, that is x greater than 5? What value does f of x approach as x approaches 5 from the left? The x less than or equal to 5 is half of things. I don't expect you to do this in your head. This is, again, one where we should use the tools available to us and take a look at this thing graphically. So, back to where we were. Let's drop into this. Okay, again, I have entered the function already, and this is a great opportunity to look at how Desmos takes piecewise functions. Up in the function entry corner, you can see that the syntax is curly brackets x less than or equal to 5 colon x plus 3 comma and so on. So the weird part about this is that it's putting the domain restriction first, then it's putting in the definition of the function. The commas fall as you might expect. They're going to separate the two halves of the piecewise. Let's take a look again at the actual behavior here, though. When we were approaching 5 from the right, that is for values that were larger than 5, so for instance from 10 heading towards 5, the function seems to be approaching -2. And when we approach 5 from the left, that is values that were smaller than 5, such as 3, 4, 0, all of those values, as we follow the path of the line, they head towards 8. So that's curious. That would seem to bear a little more consideration. Let's pull this into Notability and then mark it up a little bit. There we go. Okay, so as we said, this one right here, that's 8. This one right here, that's -2. So as x is approaching from the left, we're heading towards f of x equal to 8. As we're coming from the right, we have f of x equal to -2. So this begs the question, what is the limit as x approaches 5, right? Because there's 5. What is the limit as x approaches 5 of f of x? Well, let's go back and refer to our definition. Definition of a limit. If the function approaches some value L, as x approaches the limit from both left and right, if the function approaches some value L, the same value L, as x approaches a from both left and right, then the limit as x approaches a exists. Okay, so what we're dealing with in this problem is a situation where f of x approaches one value from the left, 8, and it approaches a different value from the right, -2. That would imply that the limit as x approaches 5 of f of x does not exist. And there you go.